In episode 10 of the Haskell Unfolder, we talked about asynchronous exceptions, which are exceptions that can be raised in a thread at any point during the thread's lifetime, independent of the thread itself is executing. In that episode, we talked about that it's important that we can mask asynchronous exceptions, which means prevents them from being raised at certain points in order to be able to do proper exception handling. What we did not talk about in that episode is that even when we mask asynchronous exceptions, they can still be raised at certain points, and this happens when we execute interruptible operations. That is what we're going to talk about in today's episode.
Welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, this show is live streamed, so I invite you to submit questions or comments in the chat, and we will try to show them on screen and to discuss them.
Right, so I want to take 5 minutes just to recap what asynchronous exceptions are and then move on from there. So, and I want to do
like a good idea, yeah.
Yeah, they are not that, they're a little bit subtle, so it's useful to remind ourselves. And I want to do that by means of recreating with MVar. So with MVar is a function that takes an MVar, and an MVar is basically a lock alongside that is protecting a value, and a function that wants access to that value, and it's going to execute that function. So what it needs to do is take the lock, run the function, and then release the lock again. And so we get the MVar, the function that we want to execute. What we're going to do is precisely what I just said, right? We're going to take that MVar, get the lock, then we're going to get some result back from this function, right? Which is either an exception or some result. And we do this inside an exception handler. And then independent of whether the function throws an exception or not, we're going to put the lock back, right? That's important. If f throws an exception, we still want to make sure that we restore the lock. And then finally, we either throw the exception if one was raised, or we return the result. And that's it. Now, this is correct in a language where we only have synchronous exceptions, but not in a language like Haskell where we have also asynchronous exceptions. And for example, this whole thing could be wrapped in a timeout somewhere, which means that timeout could be raised at any point in time. For example, it could be raised here, right? And if an exception happens here, in between these two statements, then we take the lock, and then the exception gets thrown. We're not inside the scope of an exception handler, and so we never restore the lock again. Right? So this code is wrong. And so what we said in the previous episode is that the way to fix this is to mask asynchronous exceptions. We say, okay, we only want to allow for asynchronous exceptions at very specific points during this function. And when do we want to allow for them? Well, only inside the scope of an exception handler. Right? So we're going to mask them and then unmask them once we're inside the scope of the exception handler. Now we cannot have asynchronous exceptions anywhere here. We can only have them here, and if they happen there, we will catch them.
Do you also want to recap why we want to unmask at all? Why, like?
Oh, right. Yeah, fair enough. So if we didn't unmask at all, if we would mask all exceptions, like at all times, then for something like timeout could no longer work. Right? F might be doing something that we might want to time out, and then if we don't unmask, then that can't happen. Right? So that's also not a solution. And then the other thing is that we said is that actually this pattern where we sort of acquire a resource, then do something with that resource, and then release the resource again is an example of bracketing. Right? So we can actually have the exact same function here, and we can implement it in terms of bracket instead, where the acquisition is to take MVar, and the release is to put MVar. Right? This is basically doing the same thing.
All right.
Okay. That's by means of recap. If that all went a bit too fast, then if this is the first time you're seeing this, then I'll refer you back to episode 10, where we spent the entire episode talking about this. In today's episode, I want to move on and talk about a subtlety, which is to do with interruptible operations. And I want to do this by means of example again. I'm going to define two threads. And those two threads are going to share an MVar, right? They're going to communicate through an MVar. If I can write int. So what is the first thread going to do? It's going to take that MVar and then print it. And I'm importing a local function, a local module called debug, which I've just written for the sake of this episode. It has a bunch of functions in it. Amongst others, this print log message, which just think of it as print. but with some additional machinery on top to make sure that if you have multiple prints, that they are not actually going to be interleaved, right? That they are, that we don't get messed up output. But just think of it as being print, roughly. So what does thread B do? Well, I still can't spell int. That's unfortunate. What it's going to do is it's going to wait for a bit, and it's going to wait for 6 seconds, and then it's going to put a value in the MVar.
Right.
And our main function here is going to create a new empty MVar. Then it's going to fork both of those threads, and here I'm going to use this fork debug. Comes from the same module again. Think of it as being roughly fork IO, but instrumented. And one of the things that it does is when the thread terminates, it will print a message to the console saying such and such a thread terminated. It just allows us to see a little bit more cleanly what's going easily.
And that's also what the string parameter is for, to use in that message.
Exactly. Yeah, it's just an identifier. Yeah. All right. So we've forked thread 1. We've we forked thread B here, and then we're just going to delay for a couple of seconds in the whole thing here. Okay, so let's run this. And when we see, okay, we're waiting, and actually the whole thing is printing a dot every second, just makes it a bit easier to see what's happening. So after 6 seconds.
That is not standard, right? That's also something that you added, that dots are being printed, right?
The main is just, it has this width timer thing, which just prints a dot every second. So what we're seeing is 6 seconds being printed here. And then after 6 seconds, we see that B terminates, right? It writes to the MVar and then terminates. And then we can see that A now takes that MVar and then it terminates. Right? Nothing unexpected here. Okay, good. Now, what I want to do now is I want to kill this thread, the first thread, after 4 seconds. So what I'm going to do in my main application here, my main example, I'm going to delay by 4 seconds, and then I'm going to kill thread A. This is A. Now, if I run this again, then we see 4 seconds passing. Then we see A being terminated, right? That makes sense. Then we see B terminating because it's still doing the same thing. Like it's now writing to an MVar that nobody's listening to it anymore, but that's it. And then just the whole thing terminates, right? We're still waiting the additional seconds here. Okay, also not unexpected. However, we killed A by sending it an asynchronous exception, right? That's what happened, right? We raised a thread killed exception in this thread. So what happens now if we try to mask asynchronous exceptions? Right, mask underscore is one where if we don't care about the unmasked arguments, we can just ignore it. Yeah. So you'd expect that if we do this, then now this kill thread is not going to do anything anymore because like we're raising an exception here, but we have masked asynchronous exceptions. Right? So surely this should now no longer be killed. But if you run it, we will see that after 4 seconds, that thread is still killed, just like it was before. That's weird, right? What's going on here? Now, the reason that this is happening is that take MVar is a so-called interruptible operation. An interruptible operation is one which, when it blocks, still allows asynchronous exceptions to be raised until it returns. So in particular, take MVar will allow asynchronous exceptions to happen right up until the moment that it acquires the MVar. Right, so it doesn't have the MVar, doesn't have the MVar, doesn't have the MVar. Asynchronous exceptions are possible. Then it acquires the MVar, and then atomically it changes states from not having the MVar to having the MVar, and at the same time from allowing asynchronous exceptions to no longer allowing asynchronous exceptions.
And you're saying it always does this regardless of whether asynchronous exceptions are masked or unmasked?
Exactly. Right, so that is independent of the masking state. Well, almost independent. If you really, really want to mask all asynchronous exceptions independent of the behavior of interruptible operations, you can do that. You can say uninterruptible mask.
Okay.
And now if we do this and run this again, now we see something different happening. Now after 4 seconds, nothing happens. And then after 6 seconds, we see thread B terminating, right? Thread A terminating because it got the MVar, right? And this kill thread is basically disappeared, like it had no effect. So you might wonder why right? Why is take MVar interruptible? And a key takeaway from this episode is that when you're writing concurrent code, you should always write your code in such a way that you never block indefinitely, right, for an undetermined amount of time, with asynchronous exceptions masked. Because if you do, your application might become unresponsive, right? For example, a timeout can no longer happen, right? So that should never be the case. If you're masking asynchronous exceptions, you should do that only for basically a roughly known quantity of time.
Mm-hmm. There is a question which is similar to one that I would have asked myself. So by Nikolai, what does put MVar do the same?
Put MVar does do the same. Yes.
And I guess my version of the question would be like, I guess you said something you should, whenever you're blocking, be interruptible, but like, I mean, is there a list of all interruptible operations, or how do you know whether an operation is actually interruptible or not?
For primops, the doc should tell you that. Well, let me back up a little bit. First answer is any primitive operation that is blocking should be interruptible.
Okay.
That's sort of the main design criteria. If there's a primop that doesn't satisfy that could reasonably be considered a bug. Okay. If it's a function that itself calls all kinds of other functions, then you would hope that it would document if it's interruptible, and if it doesn't document, then the only possibility is to check the source code, which is unfortunate.
But it's not really programmable, right? I mean, it's sort of a primitive property of certain operations. There is not something that you can.
Yeah, although you could make something interruptible by calling an interruptible operation.
Yeah.
So it's kind of programmable-ish.
Right.
To answer Mikolai's specific question, if you look at with MVar, it does a take MVar and a put MVar, right?
Mm-hmm.
Now this take MVar is definitely interruptible. The put MVar, on the assumption that all calls for this MVar are of the shape take and put, then we know for sure that this put MVar must succeed. It cannot block, right? Because we know that the MVar is empty. Under such a condition, this will not be interruptible. And so something is interruptible only up until it no longer blocks. And if you are sure that something doesn't block, it is not interruptible. There's one exception to this rule, but for most cases, that's the case. Okay.
So you're saying there is not sort of an infinitesimally small interval during which it is interruptible. If something can be executed immediately, like if you know you're running a take MVar and the MVar is full, you know it won't be interrupted.
Correct.
Yeah. Okay.
That is correct. Yes.
Okay.
Yeah.
Okay.
Okay. Good. So, yeah. All right. So we talked about the fact that if I wanted to make this interruptible, like truly block all asynchronous exceptions, I have to make it uninterruptible. But then I have this problem again. Now I have concurrent code, which could potentially mask asynchronous exceptions for an indefinite amount of time, right? Because this take MVar could take a long time. And so this is really only okay if you know externally that this take MVar will succeed soon, right? From some other reason about your code. All right. Now, one thing that is interesting here, if I go back to this being masked again here for a second, then it's not entirely correct to say that asynchronous exceptions can be happening here inside the body of mask. Right? They can be raised by take MVar because take MVar is interruptible, but then they are raised by take MVar. So you could reasonably consider them to be synchronous again, right? They can't be raised here or before, right? So that means that, for example, if you wanted to log when a take MVar is interrupted, for example, you could do that, right? So if I have some sort of some sort of utility function that logs asynchronous exceptions, and when they are raised, I could wrap that along like around this take MVar, and that would be correct, right? Now this is the only place where they can in fact be raised. So, okay.
No, it's like mind-bending, I must admit. I mean, because isn't the print log message itself again interruptible?
It is
that
not.
Doesn't matter. Oh, okay.
It is not. It is not.
Okay.
Yes, that is also an important thing that I can come back to later. But yes, this particular log message is not interruptible.
Okay.
Okay. Let's go back to uninterruptible again for a bit. And let's just get rid of this here. What I want to think about is, what if we do this kill thread in a thread of its own? So this kill thread, right, where we're killing thread A, let's do that in a thread itself. Maybe let's wait for 2 seconds here. And then
you want to fork, right? You didn't actually add the fork.
Yeah, sorry. Thank you for pointing it out. Now, this obviously doesn't really change anything, right? I mean, we should just see it being killed after 2 seconds. The interesting part is, what happens if we now kill the thread that's killing? Right, so we're going to wait 4 seconds in the main loop, and then we're going to kill this thread here. So this thread here, what is this doing? It waits 2 seconds and then kills thread A. Here in the main thread, we're waiting 4 seconds and then we're killing this thread. Now the question is, when does this thread terminate? All right, so let's just try it out. And we are seeing time passing. And we're seeing it terminating after 4 seconds. Okay, that kind of makes sense, right? Because, well, it makes sense-ish, but you have to think about why this is happening, right? So we are waiting for 2 seconds, and then we're killing. So why did it not terminate after 2 seconds? And the reason is that kill thread itself is synchronous. It only terminates once the exception has been raised in the thread that we're killing. That can be quite a useful property, right? For example, if I have a thread that's printing to the console, and I want to kill it and then print some sort of final done message to the console, for example, I might want to wait until I know for sure that this thread is no longer printing to the console. Right? So, but if I kill it, I know that after that kill thread statement returns, that exception has been raised in the target thread. Now, of course, we don't necessarily know what it's doing with that exception, but you would hope that at least it stopped doing whatever it was doing.
Right. So in this case, we are actually killing the thread C after 4 seconds, and that is because kill thread is blocking and therefore also interruptible, right?
Well, we haven't masked anything here, right? So there's that. It doesn't.
Oh,
really
yeah, it's not even masked. Sorry, yeah, it's not even masked. But even if it was, right?
Yeah, that's an interesting question, right? And that's the next point that I want to make.
Oh, okay.
So the first point that I want to make is that kill thread is synchronous, meaning it's waiting, it's blocking, right? But Anders is quite right. Because it is blocking, it is therefore interruptible, right? Or it ought to be interruptible, right? So let's see that in action. If I mask here, then, and I run this again, then I still see this thread being killed after 4 seconds,
right?
Even though this kill thread is blocked for 6 seconds, right? Because it is waiting for that exception to be raised. That exception cannot be raised until this thing terminates, and that thing only terminates after the whole thing finishes, right? So,
and can you do me a favor? I guess thread delay must also be interruptible by your logic, right? So if you change the 4 seconds to 1 second, then it should still kill thread C despite being
because
masked,
kill thread is blocking.
Yeah.
And so we now see it after 1 second.
Yeah. Okay.
Okay. I know this is somewhat confusing, but the key point is interruptible operations are operations that, when they block, allow for asynchronous exceptions. Kill thread is synchronous. It only returns when the thread that we're killing, when the exception that we're throwing has been raised in the thread that we're killing. Therefore, it is interruptible. Therefore, even when exceptions has been masked, when we kill a thread that is itself blocked on a kill thread, that is interruptible, and therefore we can interrupt this thread.
Mm-hmm. And sort of the justification to repeat for this whole concept of interruptibility is that operations should not block indefinitely, right? And so we should not just replace all the masks with uninterruptible masks, because then we would expose ourselves to sort of bad behavior where
you should not have operations which block indefinitely while asynchronous exceptions have been masked.
Right.
Timeout, basically timeouts. A useful intuition that I find useful is
Mm-hmm.
timeout should always be possible.
Mm-hmm.
Okay, now this may all look a bit contrived, but I assure you that this happens in real code. So I wanted to just show 2 examples of where this comes up, where this gets a bit tricky.
Mm-hmm.
So let me just paste some code in here. Suppose that we have 2 helper threads and some main application, and I don't really care what they do, so I just leave them undefined for now. And then I have some code that spawns both helpers, right? So it just spawns 2 threads, and then some code that cleans up both helpers by just killing both threads. And so now if we wanted to write this application, like my main application, I know how to do this, right? I just brackets. I just say brackets, spawn my helpers, then clean up my helpers, and then I don't really care here, and then I just run my app. This code is wrong. Why is it wrong? Well, when we are cleaning up inside brackets, right? What is bracket doing? Remember, it's masking asynchronous exceptions. It then calls the acquisition function, right? Which is this code here. Then it unmasks asynchronous exceptions again, running the application here inside the body of an exception handler. After the exception handler, it calls the cleanup function and then rethrows the exception if one was raised. Right?
But there are 2 interruptible operations now, right? Kill and kill. I think.
Exactly. These are interruptible.
Yes. Mm-hmm. Right.
So even though these are run with asynchronous exception masked, an exception could very easily be raised here.
Yeah.
If it happens, this kill thread will not happen. Right? And so we leak a resource. So this code is wrong. Now, one option is to make sure that asynchronous exceptions are not allowed at all while we're doing our cleanup. And so we could do that on Uninterruptible. Something like this, right? That would be an option.
Right.
The other option, well, this is tricky, right? Because is this okay? Is this kill thread? How long is this kill thread going to take? Remember, it's also synchronous. So now we're waiting on the other thread to terminate. So this is iffy, right? This is maybe okay, maybe not. One alternative, and this is a more useful alternative, is to fork a thread to do the cleanup. Now, why does this help? It helps because this new thread, nobody has access to this new thread, right? Nobody knows the ID of this new thread. So an asynchronous exception can't possibly be delivered to it because nobody has the handle on that thread, right? And that is quite a useful technique in general when dealing with asynchronous exceptions. That if you want to make sure that something cannot be interrupted with an asynchronous exception, one option is to run that whole thing in a separate thread and then sort of have your own communication with that thread to make sure that you communicate. Of course, it's still tricky, right, to make sure that resource acquisition and releasing is done correctly all the time, but this is a useful technique in general. Now, actually, it's not the best option here, and I'll show in a second why that is the case. But before I do that, I want to move on to a slightly separate example, which is sort of on the opposite side. So in this case, the problem was on the release side, right?
Mm-hmm.
We could have asynchronous exceptions happening here because kill thread is interruptible. I want to talk about also what happens if we have interruptible operations on the acquire side. Suppose I have something like this, where a variation with MVar, which doesn't take one MVar, but takes 2 MVars. right? And so intuitively, it should do the same thing as before, right? It should take both MVars, then run the function, and then release both MVars again, right? So actually, like the implementation should not be too surprising. What we're going to do is, let me just, sorry. I'll copy and paste rather than write it all out because it's relatively simple, right? It's the same that we saw before, right? We just take both variables, run our function, put both variables back, and then either throw or return. However, we just saw that take MVar is interruptible. That means that even though we have inside the scope of mask here, this could raise an exception. Right? This could raise a timeout exception. If that happens, we are not inside the scope of an exception handler, and therefore this take MVar would not be paired with the put MVar, and this lock would be locked forever, right? And we'd have resultant deadlock in our code. So this is very broken.
Could we not just nest with MVar though?
We can, and that is in fact the right solution.
Okay.
Yes. So before we go to that right solution, I want to make a point here that if we have something else, like say you're really working with a socket API, right? And you have an open socket and a closed socket here. Now we don't really know what this guy does, right? Take MVar as a primitive operation, right? You could just look at the documentation. But open socket could do all kinds of stuff. You don't know if it's interruptible or not. You don't know if it's somewhere inside there it has an MVar or not or whatever, right? So you can neither rely on it being interruptible nor rely on it being uninterruptible unless you know the exact implementation. So if it's interruptible, then we have exactly the same problem as we had before. If it's not interruptible, then we have the opposite problem, which means because it's opening a socket, maybe it does some sort of handshake with the other server, right? It could be a long time. Therefore, we might now be running with exceptions masked for an indefinite amount of time. Also not good, right? So in general, resource acquisition functions ought to be interruptible. And when they are, this approach of acquiring them one after the other is not correct. What we should instead do is what Andrew suggested that we do, which is bracket this thing, right? Nesting the bracketing, right? So we have a bracket for the first socket or the first MVar, doesn't really matter. Then inside there, we bracket for the second one. Why does this solve the problem? Well, if open socket is interruptible or if closed socket is interruptible, in both cases, this bracket sits inside the exception handler of the first bracket, right? So if either of those is interruptible and an asynchronous exception is raised by them, the exception handler of the first bracket will make sure that the first resource is released. Right, so this is the correct solution. Now, this is not always possible, right? We might not always have a lexical scoping, right, of our resources. We might not always be quite so clean. If it isn't, then you need to go to something entirely different. Maybe something like resource T, which is a package where you have basically some sort of external manager that keeps track of which resources we have allocated and which resources have still to be deallocated. I'll put a link to resource T in the repo, so you can look that up if you're interested. That's outside the scope of today's episode. I want to show one final gotcha here.
We have a remark.
Okay.
Do you want that now or do you want it at the end?
We can have it now, yeah.
It's by N, not M. The opaqueness issue makes me wonder whether it could have been possible to encode interruptibility in the type of the function. Yep,
I completely agree. This is a more general point actually that I wanted to make anyway. This is to my mind one of the darker corners of Haskell. It's very difficult to get this completely right at all times. So it's not, I don't feel like we have reached the best design here in the language on how to deal with this kind of stuff. And indeed, one of the things that I would love to see is that interruptibility will be tracked at the type level. I would also like that very much. That would be much nicer. Okay, just final thing I wanted to show, because this looks very innocent, right? This looks simple. But now let's consider one minor variation here. Suppose that we define this closed socket prime, right? Which just wraps closed socket, but just prints the message to the console saying that we're closing it, or just some logging message, for example. And now we have like this thing again, but instead of closed socket, we call closed socket prime. Is this function still okay or none? Unfortunately, the answer is no. Why?
Because of the put string line.
Put stir line is interruptible. Why? Well, put stir line is basically hates put stir line with, std out here, right? That's kind of what it is if I have system.io. Now, what is this thing here? std out. std out is a handle. And how is a handle defined? Well, actually, a handle
contains an MVar.
Yeah, it's like a file path and then an MVar of some lower level record, which has all kinds of stuff. So it takes the MVar in order before it can do something with the handle. Therefore, it is interruptible. Therefore, print is interruptible, right? So therefore, if we are doing this inner closed socket, then this thing here is interruptible. An interruption, and therefore an asynchronous exception might be raised. Therefore, this closed socket for the inner closed socket will never happen, right? And therefore, the second socket will not be executed. So
now I have to get back. I asked at some point, I asked about print log message or however you called it, and you said that is not interruptible. So how did you get around that there? Okay. By specifically using uninterruptible mask, I see. Okay.
Yes.
Mm-hmm. Okay.
But I think this is reasonable, right? I think this is a reasonable use of uninterruptible mask. Like we know that these log messages take little time, right? Unless we're printing an infinite data structure, right? And we don't want logging to affect the interruptibility of whatever we're putting the logging into, right? So here, I think this is a reasonable use. But but definitely something that requires a comment explaining why it is okay. Okay, that's all I had to share today. Are there any other questions that we should talk about?
No, I don't see any right now. I mean, you mentioned already, or we discussed this briefly with the type. So, I mean, I feel like perhaps not even interruptibility in the types is truly enough. I mean, I feel like one would want to test this properly, right? Ideally, if I do anything like this, I would really like to gain confidence by somehow like testing all possible scenarios. But is there something like this?
It's difficult. I'm happen to be working on a library at the moment for gRPC, which is this network communication, which is a highly concurrent language, a highly concurrent library. And I have a test suite there where I basically explore, I just have quick check generate sort of interleavings between different calls. And I have some sort of a couple of MVars in there that basically have some sort of logical clock that allows me to control when things happen. So I can generate a random order, first this thing, then the other thing, and then see what happens. That is turning out to be quite effective, but also quite difficult to get right. So yeah, testing concurrent code in general is just hard. Yeah.
Right. I mean, while we were talking, there were more questions coming in, and I think we should, because this is a complicated topic, we should probably address them. So one is by Pi. The actual output writing of put string line can also block, right?
That is a question on interruptibility versus FFI, which I think we should leave for its own episode. But yeah, that's a whole other area that I have not talked about at all. But yes, I mean, you're right. I mean, there are both interruptible and non-interruptible FFI calls. So the actual writing may or may not block as well. It depends on the exact implementation. Yeah.
Okay. And then another by not M. If you have uninterruptible mask in this put string line and you do print an infinite data structure, does that result in an unkillable process?
I
can say unkillable process, certainly not, because I mean, like on the OS level, you can always kill. But
yes, Yeah, exactly. So you can still kill the process. However, you will not be able to kill the thread from within the application.
Yeah. Yeah, I think that's all. So
Okay.
Okay, then thanks for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe, and feel free to leave any comments below. We'll leave the stream open a little bit as usual if there are any more questions right now, and otherwise, like, just use the comments below the video, and we'll try to address questions that come later via the comments. And yeah, see you back in about 2 weeks, I guess.